When trying to explain the formation of a covalent bond, it's always useful to remember that a chemical process is likely to result in elements following the octet rule. And this is a general rule that states that atoms tend to gain a valence shell with 8 electrons. Of course, it's important to remember, as with any rule in chemistry, there are likely to be some exceptions. Let's now consider the start point for the formation of a covalent bond. We're expecting two elements that both have high electronegativity values to be involved in forming a covalent bond. And because they both have high electronegativity values, we also expect the electronegativity difference to be quite small. As a general rule, we might consider a difference of less than 1.8 to lead to large amounts of covalent character in the bonding. This means that the formation of a covalent bond tends to be between two non-metallic elements such as fluorine and fluorine. As you might remember, that the electronegativity values for non-metals tend to be much higher than metals. And you can see that in the table of Pauling's electronegativity values, where the non-metals are highlighted in yellow and have much higher values than metals. So let's consider the example of the reaction between two fluorine atoms forming a covalent bond. And first of all, we'll use a simple Bohr model that shows the outer electrons in each atom. I've used dots to represent electrons on the left-hand fluorine and crosses on the right-hand fluorine, just so we can keep track of where they are after the formation of a covalent bond. Because both fluorine atoms have high electronegativity values, they're going to be pulling strongly on valence electrons. And this means they'll also be pulling strongly on valence electrons of nearby atoms. This has the effect of the two fluorine atoms being pulled close to each other until they overlap their valence electrons like this. And you can now see that there is a shared pair of electrons in between the two fluorines, which means that technically both fluorines now have 8 valence electrons. To save ourselves a bit of time and to avoid having to draw circles in my Bohr model, we can better represent this, more effectively represent this, using Lewis diagrams, where we're simply showing the outer electrons, so we can represent this same process like this. And again, the important thing here is after the fluorines have overlapped and are now sharing a pair of electrons, the octet rule has been achieved. So we now have formed a molecule containing two fluorine atoms, which would have the chemical formula of F2. However, simply stating that the octet rule has been achieved is not really an explanation for why these two atoms are now staying together in a molecule. So let's consider what electrostatic forces are taking place here to hold them together. So, to explain why, let's again draw those Bohr models, but this time showing the nuclei in the middle of the atoms. By doing this, I can see that the two positive nuclei are actually being attracted to the shared pair of electrons in between them. And it's this electrostatic attraction that's responsible for holding those two atoms together in a molecule. So the technical definition for a covalent bond is simply the electrostatic attraction between a shared pair of electrons and positively charged nuclei. Once we've formed a covalent bond, the resulting structure will be one of two things. In the example we've just seen, we formed a discrete molecule containing two fluorine atoms with the chemical formula of F2. However, for some elements, particularly carbon, we can also end up forming a covalent network structure, also known as a giant covalent structure, such as diamond. And you'll see an explanation for these in a separate video. Let's now summarize the key points. Firstly, the formation of a covalent bond occurs between two elements that both have high electronegativity values. And this means that both atoms will attract valence electrons with equal strength. Because of this, atoms will then share one or more pair of electrons when a molecule is formed. And this allows each atom to achieve the octet rule. And then what's actually holding that molecule together, the covalent bond, is the electrostatic attraction between a shared pair of electrons and positively charged nuclei. This leads to the formation of either a molecule in most cases, or in some exceptions, we find elements forming a covalent network structure, otherwise known as a giant covalent structure. And that's it for the formation of a covalent bond. Hopefully, this video is of some help.